Ever wondered how secure modern day data encryption is? The most used form of encryption relies heavily on prime factorization, and it can take years for us to get the prime factors of these numbers on normal computers. But remember, anyone having the prime factors can easily access all the data. Let's get into the details of how Shor's algorithm breaks modern day data encryption. But first, let's look at some modular arithmetic. Modular arithmetic is like counting in circles. Imagine a circle with numbers 0 through 5. This is known as a circle of mod 6. Now counting a total of 8 through the circle gives 8 mod 6, which is 2. Similarly, 10 mod 6 is 4. Now let's look at the remainders of 3 to the a mod 10. The powers of 3 are 3, 9, 27, etc., which return the remainders 3, 9, 7, 1, and so on. Notice how it forms a repeating pattern? The number of occurrences in this pattern is known as the period of the original number. Thus 3 to the 4 is congruent to 1 mod 10. After some rearranging, it's easy to see that 3 square plus 1 times 3 square minus 1 is a multiple of 10. Thus for a guess x and the number n, x to the p over 2 plus 1 times x to the p over 2 minus 1 is a multiple of n. Now we can easily find the factors using Euclid's division algorithm. In order to implement this algorithm, we need a quantum computer because a classical computer can only work with one input at a time, whereas a quantum computer can split itself into multiple classic states. That is, it can work with a superposition of inputs, but unfortunately it returns only one of the quantum states as an output. Now we set up a quantum computer with basic states a equals 1, 2, 3 and so on till n. Then we compute x to the a mod n, where a is the basic state. To find the period, we need to find the smallest a, which returns 1 with x to the a mod n. We can see that if the period of x is p, the frequency is 1 over p, and the best way to find the frequency of things is a quantum Fourier transform. But what is a Fourier transform? It is an operation to determine the composition of the wave. But for a superposition of waves, we use a quantum version of the Fourier transform. Now, if we input a state 1, we get a superposition of all other numbers which represent a sine wave. Entering a higher number results in a wave with a higher frequency. Now, entering the superposition of these states, the waves add up in some parts and subtract in others. It so happens that when we work out a Fourier transform on our base states of x to the a mod n, it returns a superposition of numbers 1 over p, 2 over p, and so on, and now it's very easy to measure 1 over p from the superposition. Now that we have found the period, we can use the maths to find the prime factors of n.